All right, so we've been talking so far about advection dispersion equation and the mechanism of dispersion. And so we'll carry on with that today, just maybe to recap what we talked about last time in terms of using models to represent the advection dispersion equation. And then, since it seems to be an important process in the subsurface of how these plumes will move, we might want to figure out how to evaluate the parameters that define it. And so I guess we explained what's going on as being our geometry, which has this chimney of residual napple with maybe some pieces of some lenses at the base where we have water flowing through it at some velocity. And what we're attempting to do is to represent that process as something as it goes downstream to represent. We said before that we're interested in diffusion and dispersion, and we treat dispersion like diffusion because it looks like diffusion. And so I guess this is our modus operandi. We don't change colors. That looks something like this. And we describe this behavior in terms of this advection dispersion equation. Accumulation is equal to longitudinal or mechanical dispersion. The advective term, and I guess a transverse dispersion term, dt. And just to firm up what we mean by that, I guess if we look in plan view on this, as you pass that around, we've drawn all these diagrams before. We kind of represent this process by a one-dimensional flow system that looks like this, although we know how to represent multi-dimensional ones, three-dimensional ones as well. And I guess we know that this is equal to diffusion portion plus alpha L advective velocity in the x direction. And we know that this is kind of corrected from our diffusion coefficient out of a chemical reference book multiplied by some factor to represent the tortuosity that is going in long grains, and that this is due to mechanical dispersion, and so this is the advective velocity, and it would of course be in the x direction because there is none in the y direction. It's 0. And we can use this equation to describe our behaviors. And last time, we merely, if I move that up a bit, yeah, maybe it's worthwhile drawing these just to because it kind of cements our understanding of things. So I'm going to cheat. I'm not going to cheat, but I'm just going to draw our system time, concentration. Concentration is a vertical axis on all of them. This is time. This is x. I guess I'm going to cheat now by doing this. let me do it, so I guess I won't. Don't know why I can't duplicate them. I can do it otherwise. It's just clearer to draw these plots out separately and spend a bit of time doing this at the beginning of class, just to make sure everyone is on board. And that was that our function here, well, our input function looks like this. This is our core. Our distribution looks like this. If our input is just a pulse, so this would be 1, this would be 1, then I guess this would look like this. It would be identical, and that you know the coordinates for the different features. I guess velocity is equal to length over time, so time is equal to velocity times length. So this would be time is equal to the product of advective velocity times length. This distance to the front would be equal to length being equal to time is equal to length over velocity, right? Yep. And length is equal to velocity times time. And so that's kind of fine for our simplistic view. And it would be fine if it was plug flow. But we also talked about the fact that if we have dispersion, then these curves start to look like this. Don't know what that is. Nope, that's not what it looks like. Oops. And this. And I never drew the figure of why that should look like that, but it's kind of, if you imagine, I suppose you could draw it here, you could think of a part of this porous medium that we take out here being a front that looks like this. So you have these little tendrils that look like this. This would be our contaminant. And I suppose if you draw a line across here, you'd have some, if you average this, you'd have some concentration that isn't 1 or 0, it's part way across it, and therefore it represents these fingers, the tendrils that go ahead of it. So physically that's what's going on. And so the mechanics of dispersion are that if you think of it going down these fast highways, then it spreads it out more than it would do otherwise. You don't get plug flow, and then you have to deal with it. And we talked about the cases by which we can use our model, and we came up with this relationship which allowed us to define this equation in terms of 2 extra non-dimensional terms. One was a Peclet number, which is an advective velocity times a length divided by dispersion coefficient, and a Courant number, which we'll call TR, which rather than CR, which is a velocity times time over a length. And so we could convert this equation into using Buckingham pi and all those good things, and we could plot these two curves on the right hand side, which of course these are residence time distribution curves. And in terms of TR, T sub R, and for plug flow it would look exactly like this. And for non-plug flow with dispersion, it would look something like this, and also like this. So this would be a Peclet number of infinity. This would be a Peclet number of, I don't know, 1 and 0.1. And I told you last time we didn't have I'd lost my access to GNU plot to be able to do it, but I guess I forgot that I actually have this other thing called Equasio, right? So this is actually pretty slick. Am I able to move that up? Am I not able to move that up? Well, I guess I did have it. Why can't I get it to do that? Let's quit. Let's go back in. I guess you guys have access to this as well. Just thinking, it's there somewhere. So I'm going to take this little latex equation. And here we have it. Let's see if I can manage to make it do this. Can I change the scale in any way? I guess I can change the scale by doing this. So this is Peclet number. So this is the advection and dispersion equation solution, which is in Fetter, which we looked at last time, which would be exactly this expression here. Thank you. This expression here. Peclet number, Courant number, etc. And this is just showing exactly what happens if we mess around with Peclet number. So Peclet numbers, Peclet number of 10, let's do it larger than that. Doesn't like Peclet, can't get Peclet number of infinity, but you see the coordinates of this. This is relative concentration on the vertical axis, 1, 0. This is pore volumes, so TR equals 1 means one complete pore volume is pushed through the core from its entry to its exit, and we're measuring the concentration at the exit. And at a Peclet number of 100, the 50% concentration is exactly at 1 pore volume. This part here is due to the fingers that are going ahead of it, and this are the fingers of water that have no contaminant in them that are behind it. If we change the, I don't know why it doesn't let it do that. Will it do it as a larger number? Doesn't like that 0. Doesn't seem to mind that. I don't know why it wants. That's 600. As you see, we increase the Peclet number, it gets sharper. And as we reduce the Peclet number to 1, you see that this is the 50% concentration mark. And now the curve has deviated from this kind of Heaviside function that goes up vertically at this point, and now it's moved over. If we reduce it further, it just goes flatter and flatter, 0.1. Looks like this, and I guess if we add some zeros ahead of that, it has this strange shape. And so it has this strange shape because we're defining it relative to the number of pore volumes. But if we have diffusion operating, then it doesn't care about the number of pore volumes because it's acting completely independent of that and is diffusing to the end of the system. So that's just a way of being able to define this behavior. So that kind of sets the stage for what we'll talk about today. So that's the expression that we're trying to represent. And now I guess we'd like to be able to do some things to understand exactly how we might evaluate it. And we could think about using laboratory methods. We could think about using in situ methods that use well testing once you've drilled a hole. And we could think about using what are called natural gradient tracer tests. And we'll talk about them each in sequence. I guess the conclusion we'll come to is that maybe the only one that's possibly useful to us is the last one for methods that for reasons that we perhaps will highlight. So this is the idea. We talked about having this behavior along a one-dimensional flow path. We know that in reality our flow paths maybe will have spreading in them. And so we could think at least intuitively what the consequences of this lateral dispersion would be. And I suppose if you're not constraining it to follow a single path along a tube, if you allow it to disperse laterally, then you could imagine that you're reducing the concentration in the middle because it's dispersing outwards to the sides. And so the concentrations you'd have within this main plume would perhaps be reduced spatially. And so if you took a section across it and you looked about it being constrained in one dimension or two dimensions, then and allowed it to spread laterally, then you'd see that maybe the concentrations would get less far downstream because it's also expanding out laterally in plan view. So this is a slice through it. If you looked in plan view on top of this migration direction as it goes downstream, then if it's expanding laterally, you'd expect this concentration front at the tip may need to be retarded from where it would be otherwise. So we could expect that to be some representation of that behavior. And this are just results from FETA that kind of show that for a cross-section through a landfill, that you could have chloride concentrations, which is a conservative tracer, being advected downstream. And the form of this plume is strongly controlled by the magnitude of lateral dispersion that you get. So this is longitudinal, this is transverse dispersion. So 10 meters, 0.1 meter, 0.01 meters. I guess this is 1 meter, not 10 meters. So as you get smaller and smaller dispersion, it's more concentrated into kind of a one-dimensional profile going downstream. If you get more and more lateral dispersion, you'd expect the downstream tip of this to travel less far, and it would travel more out of the page at you. So those would be practical consequences of what would happen. So it seems important that we might want to know something about what these magnitudes of dispersion coefficients are, because these are the magnitudes that go into this expression through this term here and define the mechanical dispersion through these two terms. It's just the indexing parameter. So how can we do that? Well, you can imagine an obvious way to do it would be to take a core, to have an upstream boundary condition of concentration, and measure the breakthrough at the downstream end, be able to write out the expression that we already wrote out, which is basically this. This is the previous expression that we just looked at on equatio, with one term at the end of it slightly reduced. And if you push through a number of pore volumes of fluid, so if you push through half a pore volume of fluid, you could measure the concentration at the downstream end of the core. You push through one volume, you measure the concentration, etc. So you'd end up with a residence time distribution which at half a pore volume, 0.75, one pore volume, 1.25, so you'd get these concentrations. And this would allow you to get a magnitude of Peclet number. Peclet number is equal to advective velocity times length over dispersion. You know the length of your core because it's in your lab. You know the velocity that you're forcing water down it at because you're providing a gradient between the upstream and downstream, or perhaps you're using a peristaltic pump to do that. And so you have this. We said that all these different curves are a family of curves, so it would only fit on one family, hopefully, and that family would be a unique value of Peclet number equals, it's not infinity, maybe it's a Peclet number of 1. I don't know, we could go back to Equatio and look at it, and if you know what this Peclet number is, then the only thing you have left to find out is this. If you know what this magnitude is, then we know that the overall longitudinal dispersion is equal to diffusion coefficient times tortuosity plus advective velocity times alpha t. This term here is dl, which is really what you're measuring here, because we're assuming that we have a velocity big enough that this diffusion coefficient is essentially 0. So this is what we're measuring. We're assuming this is 0. And then if we know the velocity, we have alpha t. And so we're able to get it that way. So that would appear to be a good idea, but it's actually a lousy idea. And the main reason for it being a lousy idea is that if we refer to this picture we drew here, right at the base of this page, that the concentration of our plume is due to these little fingers which are going ahead. If we think about the reasons for these fingers, I suppose we could think that the reasons for these fingers are little lenses of coarser material, perhaps, that is allowing the velocity to be faster in these superhighways than it is in the material that intervenes, though. And so if we have this structure in our core, which is representative of a much bigger scale, where we'd expect it to be at a much bigger scale, then the test that we've done in the lab would be perfect. But if the structure that we have in our core isn't really representative of a large-scale structure in situ, then our experiment is probably not going to be very representative of our real-scale dispersion. And so this might not be a very good way of doing that. So the next step would be to take it out of the lab, where you're not dealing with a small scale anymore, and try and take it up the next step to talk about doing it in the field, where perhaps you do have this structure at the right scale, meter scale or larger scale, the scale of your plume in place, or the plume that you expect to develop in place, and then run an experiment. And so the corollary of doing this experiment in the lab would be to have a well, to push a concentration, water with a certain concentration in it, so that out from the well bore, I guess, if we drew a picture like this, this would be a radius or an x. This would be a concentration. And I suppose the concentration would look like this at time 1, this at time 2, this at time 3. And it would be going out, these would be the traces at each of these times, right? 1, 2, and 3. And that's fine. And so we've kept it going in at a given concentration, and then at some time we stop pumping it in. And at that time, then we start sucking it back out. So I guess we've pumped in, and now we're going to suck it back out. And so what we'd expect it to do, we'd expect this one at 3 to go back to 2A, this one at 1 to go back to maybe 1A. And so I suppose if we followed behavior in the well itself, I'm kind of running out of space. C over C, 0, and time. So this is space and this is time. So as we pumped it in, I'm going to, what would it look like? I guess in the well bore, we'd pump it in and it would look like this, right? So at time 0, it's a concentration 1 in the well bore. Time 1, 2, and 3, it's still concentration of 1. So this would be time number 3, 2, and 1. And then if we start pumping it back out, what would we expect to get? Well, we'd get it at the same concentration, but at some stage it would start sucking water out, which is beyond this outermost reach. So I suppose we'd get a residence time distribution, which would look like this. Well, if it was plug flow, it would look like this, right? And if it had dispersion attached to it, it would look like this. And so we could imagine that from this geometry, by looking at this residence time distribution curve from sucking it back out, then if it was very sharp, then the dispersion would be small, and if it was canted over very significantly, then the dispersion is large. And so if we can quantify that in some way, essentially the same way as we did in a laboratory, by running it at a given velocity, we know the velocity we're pumping it in at, so we know the advective velocity, and we know the velocity we're pulling it back out at, then if we can fit it to a curve, then we can get a value for alpha t. And so this would be just rewriting Fetter's curve from what we talked about last Thursday, and really what we used today, this equation here. It has some extra terms in it for exponentials, but it doesn't really matter. Then we could try and fit this analytical curve to what's going on here, and as a result of that, we could pull out the value of this longitudinal dispersion. And so the other spoiler on this is this isn't any good either. And so the thing that makes this not very good is the fact that, one, it's not really the scale of the plume, because if it was the scale of the plume, it might take us a long way to get it that far out. And the second part is that it has what we might think of as artificial dispersion. And so if you think of looking at this in plan view, and you think about the streamlines that you'd have, we talked about flow nets, I guess, in a prior life. A flow net that would represent this behavior would look exactly like this. These would be lines of equipotential, equal pressure head, because you're driving flow. These would be individual lines that the individual water particles and contaminants would take on these rays. You see that as you go from this point to here, you must by definition have a big velocity in this point and a relatively small velocity here, because it's going across a bigger cross-sectional area, just by continuity, right? Same volumetric flow across each of these interfaces. This interface is small, so the velocity must be large. This interface is large, so the velocity must be small. And so you have what you could imagine is geometric spreading just due to the flow geometry, if you like. And so that geometric spreading will give you artificially elevated values of these longitudinal dispersion coefficients. It's perhaps not so obvious in this geometry, but it is more obvious in this geometry, perhaps, I think. And so the corollary to a single well tracer test, a push in and a huff and puff, as it might be called. So you pump it in and you pull it back out, push-pull or huff and puff, would be a twin well tracer test. So here the idea is that you take the tracer, you inject it into this injection location, you have a higher pressure here than at your downstream well bore. So I guess between these two locations you'd have a pressure gradient. And so if we plotted in X, well, it could be a water table, I guess. You could probably think of it as a water table or a pressure, same thing. This could be the water table, or this could be a pressure gradient, because we know that advective velocity is equal to k over mu porosity dp dx, right? Higher pressure here, lower pressure there, dry flow. And so if you think about the streamlines that would have, this is basically a flow net that would describe that. The only requirements of a flow net are that each of these cells, as you remember, must be roughly equidimensional. The width and the length of the cells must be roughly the same. And if it satisfies that requirement, we could exactly calculate what the flow is in this, right? The volumetric flow in this would be equal to number of stream channels, number of drops, hydraulic conductivity times the head drop. So if this is P, the head drop would be equal to what? It would be equal to this pressure, delta P divided by the unit weight of water. The hydraulic conductivity would be whatever we prescribe it to be. The number of stream tubes would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 6. I didn't draw the ones on the bottom. So this would be roughly 10. And the number of drops going from here to there would be 1 drop, 2 drops, 3 drops, 4 drops, 5, 6, 7, 8. Not bad. So I don't need a model to calculate that. You could directly calculate what your flow rate would be through here. You could also directly calculate what your flow velocities would be through here. And from what we've said before, the velocity, the time for it to travel from this point to this point must be fastest along this pathway, right? Because the pressure gradient is highest, and you'd expect that to the case. And the residence time to get from this well to this well by going in this direction, here, to minus infinity or to plus infinity in this direction, and then back in the other side from minus infinity back in here, the residence time distribution on this stream pathway is infinite time. And so the fastest one would be on the direct path. This would be slower. This would be slower still. This one would be even slower, and this one would be even slower. And so you could think of this as an exact representation of what we talked about before about geometric dispersion. So the arrival time on this flow pathway will be first. These are the individual travel times given by this expression. They vary with the angle theta. The fastest one will be theta equals 0, because this term will be equal to 1 minus 1, so this will be 0. And I think this will be 0 here. Sine 0 is 0. So 0 divided by 0 is 1, and therefore the residence time on the fastest pathway will be just equal to this term here. And so we could think about plotting it up. This would be the fastest arrival, which would be this pathway that goes here, and all the other ones would look like this. And so the only point in saying this, if this was continuous injection, then the continuous injection, the arrival profile would look like this curve here. And that would be for plug flow. So if you can imagine plug flow on each of these trajectories, the fact that they have a staggered arrival that would give us this curve means that exactly as a result of our flow geometry, our arrival times are conditioned not by anything, it's not saying anything about dispersion due to mechanical dispersion in the porous medium, it's saying everything about dispersion due to this flow path, which is non-homogeneous. It's fast flow here, slower, progressively slower as each of these goes out, and this artificial dispersion due to the flow regime is manifest in this, even if it's perfect plug flow in each of the flow channels. I suppose if we thought that on top of that perfect plug flow it had some mechanical dispersion, then our curve would look like this on top of it. And so this is with no dispersion. So it's not like our previous ones where with no dispersion we've had a really sharp front that's cantered over like this. Here we have a flaky front that's due to the effects of the flow regime. And so if you have that added effect of the geometric dispersion due to the flow regime, it makes it tough to pick out any superimposed dispersion due to this mechanical dispersion of the porous medium. And so that as well, if we go back to here, doesn't work out very well in terms of using it as a well testing method. And so the other thing which we didn't talk about is that in addition to that mechanical dispersion, I guess geometric dispersion, it also has a high flow velocity. Running out of space. And so for the huff and puff experiment, where you inject water in and suck it back out, and actually for this one as well, in the lab, and for the case where you set up this artificial pressure gradient, then you're setting up a much bigger flow gradient than is present naturally in a natural gradient flow test. And so since dispersion is conditioned by that in a way that we don't completely constrain, right, because of this, I'm not trying to make you sick by rolling backwards and forwards, because it's constrained by this function as a function of velocity, then we'd like to do our experiments as close to the real natural gradient in situ to be able to get a handle on that. And so that's the last form of an experiment that we can think of, is a natural gradient experiment. And so that would be such as this. And so this is an example that's taken out of Fetter. It's in a place called Borden in southwestern Ontario. It's Canadian Forces Base. Perhaps they're the guys shooting the balloons down over the weekend. And this is a purpose-made experiment, not a naturally contaminated site. It's a sandy aquifer, and so what they've done is they've gone in and they've released a cocktail of which this is just one component. This is actually the chloride ion being monitored. It's a relatively shallow depth. I don't really have any pictures to show, but it's a sandy aquifer. It's been introduced artificially. It has a natural gradient that's carrying it downstream. And this stuff that's been introduced has merely been followed over 2 years to see exactly what the form of the downstream cloud looks like as it evolves downstream. So after 3 months, after a bit over a year, and after about almost 2 years, it's looked like this. The way it's been monitored is by just sticking in capillary tubes, maybe 1/10 of an inch diameter steel tubes into the ground and sucking water out to be able to get the concentration at a point in here, and therefore reconstruct this contour plot of the plume. And what we can do with this is that since this is moving down gradient at whatever the advective velocity is, we have a chance to be able to use our expression to define this. And what we could do is we could take the center of mass of each of these plumes. So after 85 days, the length it's traveled down gradient has been 9.5 meters, which is this. After 462 days, it's gone down 38 meters, etc. So we can tabulate each of those here. We know that velocity is equal to length over time. So we can get that directly from these two values. So if you divide 85 days by 9.5 meters, or vice versa, I guess, 9.5 meters by 85 days, you get 0.11 meters per day. So you get the velocity just from looking at the center of mass of this plume as it goes downstream, and gets a value of just under 0.1 meters per day. We know that what we talked about last time, the geometry of our plume, if we look at it in terms of actually I didn't really want to draw this upside down, but if we draw it in terms of a Gaussian distribution, it looks like this. Bad drawing. This is 3 standard deviations, what we call 3 sigma, and it's a physical length. The half plume length is a length. This is C over C0. This is a length. And so if you measure the half length, well, at 85 days, I'm guessing that this is 5 meters here, just from this scale. So this length here is roughly about 5 meters. This length here, if I take the center of mass here and draw half the length, I don't know, I have it down as 15 or 14 meters here. So this is 14 meters. This is 5 meters, etc. And we know from this expression, 3 standard deviations is this half length. 3 times the square root of time when it was observed times the dispersion magnitude allows us to be able to solve that equation for d sub x. So we can solve for this by just substituting in the value for this and for this. This whole term, by the way, is 5 meters, and this would be 85 days. It's consistent in terms of units, and we get a magnitude of dispersivity from it, which is this. And if we wanted to, we could do that for the transverse dispersivity. So if this is a plume in this direction, we could also look at the plume as this. This would be 3 sigma in this direction, which would just be this width here, which I guess is 6 meters from this. Same calculation. 6 meters, it occurs after 462 days, which is this here, and allows us to get the transverse dispersivity here. And then if you do it for all 3, the averages come out to be this. So this is about 0.02. This is about 0.01. Smaller, perhaps expect it to be. I suppose if you looked at it, you'd expect it to be smaller because this is quite elongate compared to its distance across it. So you'd expect it to be smaller for that reason. And we can get these magnitudes out of this. And so that's one way that we can get this. If we know now, if we go back to the same expression as before, that the longitudinal dispersion is equal to diffusion times tortuosity. So this is the reference manual magnitude relative to the magnitude of mechanical dispersion. This is going to be 0. This is longitudinal dispersion times the advective velocity in the x direction. We have everything we need here. This is what we have. We also know what the advective velocity is. The average is this. And so we can calculate a value of alpha L if we wanted to. And so we're treating that as a fundamental parameter that describes the, I guess, the heterogeneity of our aquifer. If we think that this description that we talked about before, that these superhighways are the reason that we get spreading ahead of the front, is that because we have pristine water in here, we have contaminant traveling ahead of the front in this little lens. On average, it looks like a value which is arriving early because ahead of the front. In space, it would be this point here, a low concentration. This would be 50% because it would be at 100% concentration here, but only 0 concentration here. The average of those is 50%. And once you get inside the plume into this point here, then we're at 100%. So that's the explanation of this. So we think that this term, alpha longitudinal, is some measure of the heterogeneity, if you like, of these flow paths that gives this spreading. And that's what we're trying to measure. And so we think then that if we're doing this in a real field site, if we're doing it at the scale at which the plume will occur, and if we're doing it at the velocity at which it's being carried downstream anyway, then it might actually be representative of our system, at least for those conditions. So the third of our cases, lab measurements, perhaps not so good, wrong scale. In situ measurements at unnatural gradients, not so good because the gradient is high and it might not be big enough to accommodate the full scale of the plume. And then finally, the third one is under a natural gradient, therefore representative, and also at a scale at which we might expect it to be representative of the plume itself. And so perhaps the best of all our worlds. So does it turn out to be that? It turns out to be strange. We alluded to this last time. We made the case that maybe the value of this longitudinal dispersion is equal to the plume length divided by 10. So maybe we don't need to know anything about our aquifer at all, because this has nothing in it that says anything about the specifics of the material that is comprising it. And the idea is this. These are measurements taken from a whole bunch of plumes at a whole bunch of different scales. The scale would be, I suppose, the length of the plume. We've drawn it as this multiple times, right? Whoops. So I presume, well, don't presume, the length of the plume that we're talking about is this. So this is the amount of the aquifer that's sampled. If it's early in its life, it's sampled only a little bit. If it's later in its life, it's sampled a much bigger part. And so these are plumes that are sitting at that size, whatever size they are. Maybe they've been in place for a year, 10 years, 100 years. And these are the magnitudes of the longitudinal dispersivity that have been calculated for those aquifers from the shape of the plume after that amount of time and the scale of the plume. And this line here is the best fit across that. And alpha L is equal to length over 10. So this is length on the bottom. This is alpha L on the side. And this is just the equation of that straight line. When the scale is equal to 1, is equal to 0.1. When the scale is equal to 10, it's equal to 1. So it obviously fits this equation for the straight line. And I guess you can see two things. One is that if you have a given plume, say your plume length is 10 meters. Actually, let's say our plume length is 61 meters. So 61 meters would be something like this. So this would be the value here. So alpha L would be equal to 6.1 meters over 10 equals 0.6 meters, which would be the prediction from this equation. And I guess you can see also that there's a pretty big spread on this, right? The spread on this is between 100 and, I don't know, is this 200? Not quite 200, I don't think. And this is about 0.2 meters and 200 meters. So 0.2, 2, 20, 200. So 3 orders of magnitude spread for this, 1,000 times. So maybe that's not a good omen. So we can use this line that goes through this, but you have to realize that it's a shotgun blast on the barn door in terms of the spread of these. And so although this might be a good characterization of what's going as a line through the center, there's pretty significant outliers on either side. And the reason for using 6.1 meters was in this, or 61 meters, is that the size of our plume, the largest size of our plume is 61 meters. So the alpha L that we'd predict for this would be 61 over 10, which is 6.1 meters. If we take the value that we got for this, which is a dispersion of 0.02 meters squared per day, we can convert that into a scale. Well, this is the calculation here for a plume that's 6.1 meters long, multiplied through by the advective velocity, which we had on the top of this page here, which is 0.1 meters per day. We end up with a predicted dispersivity of 0.55 meters. So by using that equation of a tenth of the length of the plume, we end up with a magnitude of this, 0.55 meters squared per day. If we use this natural gradient test, we end up with a magnitude which is 0.02, which isn't very close. Which I guess is this value down here. And so the reason, that's a equal sign with a line going through it. So it's not very close, and I guess the reason for it's not very close is because the spread on using that approximation, useful as it is in terms of defining the process, that it's not really related to the porous medium so much as the scale of the plume is that there's a big spread on the predictions that would come from that itself. So using the mean value is fine, but it could have a spread roughly an order and a half magnitude on either side of that. So that's it. So we can use that expression, which is kind of identified here, and it's probably useful for us to do that, but we have to realize when we're doing that, one, the reasons that it applies, because you could think of this porous medium as being a fractal dimension, or a fractal medium. Fractal medium means that the porosity in it is the same at all scales. So if you have at small scale the chance to have a small fracture, then at big scale you have a chance to have a long and big fracture. And so the big fracture you'd think at a larger scale would allow you to get much more dispersion. And so this is merely an indication of the porous medium as kind of a fractal medium and represents heterogeneity is at all particular scales. And so we'll leave it at that. And the final figure, I guess, we've never talked about this, but this is also in Fetter. If we go back to these pictures that we drew here, we talked about a constant supply would give us a breakthrough curve that would look like this. We talked about the fact that a sudden injection and then no more injection of a pulse would look like this in the aquifer and then look like this in the residence time distribution. We only drew the residence time distribution in a dimensionless plot for this case. We did it last time with the Fetter's equation. It's not Fetter's equation, but it's the equation we had. We can also get a residence time distribution for this kind of geometry. And the residence time for this geometry in terms of the pore volumes, where this is one pore volume, is this last figure on this last page. It's in Fetter, which you don't have, I know. And it scales merely the way that we've talked about it. If the Peclet number is huge, then it represents one pore volume. I guess if the Peclet number is infinite, it would actually be a skyscraper. It would be on this, at a pore volume of 1. If it's 1,000, it's slightly flattened. If it's 100, it's flattened. You see that they all go through a relative concentration C over C0 of equal to 1. This is not the Courant number that I talked about. and this is just scaled for the maximum value. You realize that it can't be equal to the upstream value for the reasons that we talked about here, is that the area under this curve has to be a measure of the mass of solute in the plume. It's finite, and it isn't continuously supplied, so by the time it gets downstream, this magnitude here can't be at a value of relative concentration. This one can be. This could be 1. This dispersed one cannot be, because the mass under this green area has to be the same as the mass, the area under here. And so this concentration has to go down. And so if you look at the residence time concentration, that has to be reduced as well. And so this magnitude that we have here is not equal to a relative concentration of 1, because it has to go down. And you see that as the Peclet number gets smaller and smaller, this is where advection and dispersion are the same as each other by definition. Then you already see that the arrival time is much earlier than a pore volume of 1. It's a pore volume of 0.4. And so this suggests that it kind of arrives earlier because of diffusion, but this is a wonky reference frame, because actually it's arriving, there is no residence time distribution, because this is mainly being driven by diffusion in the aquifer. So this is the corresponding curve that we had for the residence time distribution from before, which was TR and so this is they're the equivalent of each other for these two different distributions. And so you have those. So I guess that's the last slide that we'll talk about. So far, we've talked about advection dispersion equation, what it represents, and we've made the point just recently in this last little foray that if you look at the area under this Manhattan distribution, it's conserved as you go from upstream to downstream. And so as this plume moves along the length of the core, as it progressively moves along, if you had more and more dispersion, then this would just get progressively flatter and flatter. So if the dispersion here was higher, then this would be magnitude dispersion progressively increasing. But the area under this gray curve would be kind of the same as the area under this red curve here and under the green curve here. And so that represents what we refer to as conservative transport. The amount that you start off with in solution here stays in solution as you go downwind. But what could happen is that the solute could interact with the porous medium, sorb onto it, and if it's sorbed onto that porous medium, such as in carbon within that porous medium, then it would be lost to the flow field. And if it's lost to the flow field, then the amount under each of these curves would not be the same. The area under these curves would not be the same. So we need to talk about non-conservative transport. Non-conservative transport is when some of it is plucked out of the flow field, attached onto organic carbon or onto the surfaces of the grains, and therefore isn't in the water for you to drink. And so the next topic that we'll talk about is non-conservative flow. And actually, if you wanted to talk about non-conservative flow in 2 seconds or less, which you might not want to, but I will do it anyway, because it is 2 seconds, is that we could define something called a retardation coefficient, which defines how much of the material is sorbed onto the porous medium. And it turns out that if you can define this retardation coefficient, which is a function of the sorption, then you can recast the advection dispersion equation just by dividing your coefficients in terms of this numerical coefficient, which is a number between 1 and infinity, and it just scales the advection dispersion equation, which means that all these relationships that we've developed so far can be used for these non-conservative flow fields just by scaling our dispersion coefficient and our advective velocity, and everything else falls over. So what we'll do next time is we'll try and figure out exactly what the features are that sorb material onto the porous media. We'll try and define them in terms of what the magnitudes of that sorption would be and how it relates to R. And then we'll talk about how we can then use the advection dispersion equations to say something about the arrival times, which you could guess that from what we've talked about, a retardation coefficient might mean that the arrival times might be equal to, what do we say the arrival time would be before? Time would be equal to time is equal to length over velocity times retardation. And length is equal to velocity times time divided by retardation. So what it does is it simply scales our physical understanding of what's going on. So it moves more slowly because it's retarded in space. Therefore, the plume doesn't travel as fast. So if you take a snapshot at a given time, this would be a conservative plume arrival. This would be a retarded plume arrival. If we look at the residence time distribution, then the arrival would be retarded. So we can just take our very simple advection dispersion plug flow equations, and we can just add an extra term, and everything washes out. Everything washes out, except we still have to worry about the case that, not always our 50% arrival time is at one pore volume. And so we have to reconcile that. But it will be correctly predicted if we use these conversions. That wasn't 2 seconds, was it? I realize that, but anyway.